Okay, any other questions? Please settle down. All right. So in the last class, we saw these two different notions or definitions of the derivative of a real valued function, right? The main point of giving the second definition is because we want to be able to extend this idea of a derivative to higher dimensional functions, right? More general functions. So more generally, in fact, so as long as you have an arbitrary function from Rn to Rm, it can be from one space to another, any metric space to another metric space, we can define the derivative. Yeah. So let the class be a little more silent. All right. Okay. Right. So the goal is to extend this idea of a derivative to an arbitrary metric space, or at least over higher dimensional spaces. Right. So suppose we have a function f from Rn to, let's say, Rm, right? Then how do we define the notion of a derivative, and what does it mean for a function to be the derivative of another function, right? So I'll give an abstract definition of a derivative first. We'll see how do you compute the derivative of a function, and then we'll see what is the geometric interpretation of the derivative. So I'm given a function f from Rn to Rm. So we say that this function f is differentiable at a given point x. If we can find some function, right? So some function, let's call it df of x. So what is this df of x? So I can think of df of x as another function from, let's say, Rn to so this is, so if f is a function from Rn to Rm, then df is going to be an m by n matrix. All right, so it says the following happens. So if I take any y that is arbitrarily close to x, so as I take an arbitrary y and let it go closer and closer to x, then of course if f is continuous, then f of y is going to get arbitrarily close to f of x. All right, but then at what rate does it get close to f of x? It goes close to x at sort of a linear rate that is given by df of x times y minus x. Right, so this divided by norm of y minus x, this should go to 0. All right. So first, let's just make sure that this definition is even consistent. Note that f is a function from Rn to Rm, right? So f of x is going to be an m length vector. You can think of f of x as an m length vector, right? So f of y is going to be an m length vector, f of x is another m length vector, and df of x is an m by n matrix, y minus x is an n length vector. So at least the dimensions all make sense, they're all correct. All right. So let's compare this with the one-dimensional case. Suppose I have a function from R to R. What does the above reduce to? Right. So what would df of x be? What would be the dimensions of df of x? So 1 cross 1, right? So in the one-dimensional case, this asks for limit y tending to x of the norm is simply the absolute value. So this is mod f of y minus f of x minus some df by dx. So let me call this f prime of x times y minus x whole divided by absolute value of y minus x. This should be equal to 0, right? An alternative way of looking at this is if I represent y as x plus epsilon. Note that epsilon here denotes a small quantity, need not be positive, could also be negative. I could essentially just rewrite this as limit as y tends to x, epsilon should tend to 0. So this is limit as epsilon tends to 0 of f of x plus epsilon minus f of x minus f prime of x times epsilon whole divided by epsilon. This should be equal to 0. Right, so at least this definition that I gave for the higher dimensional case, at least it reduces to the one-dimensional case. It's the same as what if I look at functions from R to R, then this definition simply reduces to the earlier definition that I had. Right? If you're worried about whether this should be epsilon or mod epsilon, it doesn't really matter. It is just that I want both the numerator and the denominator to be real numbers. Right? That is why that's the only minor definition. That's the only minor difference. But this you can show is essentially equivalent to this particular quantity, because anyway epsilon is tending to 0 and the right hand side has to be equal to 0. All right. Any questions? Yeah. Correct. So ultimately this particular definition would I agree, it would depend on what norm you choose, right? In the one-dimensional case, we typically take absolute value of the difference. Not your own positive quantity, it has to be a norm. It has to be a norm. That's it. You can choose any norm you want. That doesn't matter, right? But it has to be a norm. Yeah. I'm sorry? Y is an n length vector. Correct. No. So y and x are both in Rn. Right? f of x and f of y, these are in Rm. Okay, good. Any other questions? Okay. Not any pair of norms, but in most cases it is true. Yeah, in general, if it's differentiable with respect to an LP norm, it's differentiable with an LP prime norm. But you can't take any arbitrary norms, pair of norms, and make the same claim. In most cases, we'll only be working with the L2 norm, right? But this is a more general definition. And we'll make use of the general definition only in certain specific examples, but for the most part, we're only going to typically going to look at functions from Rn to R, and the norm that we will deal with is L2 norm. But in certain special cases, I'll make use of the more general definition, right? Any other questions? Okay. So let's just take an example, right? So what would a general function look like? So suppose f is from Rn to Rm. F of x is just, you can write this as a vector, right? So the first component of this vector is some f1 of x1 through xn. The second component would be f2 of x1 through xn, and so on, right? And here is an example. So suppose I have a function from R2 to R3. This is what it might look like. So the first component could be, let's say, e to the power x1 plus x2. The second component would be x1 plus x2, and maybe the third component is x1 minus x2. All right, it's just an example. All right. Now you're used to, you know how to define or how to find the derivative of most common functions from R to R. How do you find the derivative for an arbitrary function from Rn to Rm? Right. The useful property that we will make use of is that if the derivative exists, then the derivative happens to be the Jacobian, right? And you recall what is the definition of a Jacobian? Simply the following function. So it's a matrix, it's an M by N matrix, where the first component is dou f1 by dou x1, the second component is dou f1 by dou x2, f1 by dou xn, dou fm by dou x1, dou f all right. So it's enough to just evaluate the partial derivatives. That gives you the Jacobian, and hence you can find the derivative. Again, this works well as long as it's looking from for functions from Rn to Rm. Any Rn to any Rm for any m comma n. This is how you can compute the derivative. All right. Any questions? Question? Well, typically we'll work with functions for which df exists, right? Sometimes it won't exist, I agree. But another way of finding whether df exists and whether it's equal to the Jacobian is the following. If all of the partial derivatives dou fi by dou xj exist and they are continuous, then the df is equal to the Jacobian. So that is an easier test to say whether the derivative is equal to the Jacobian or not. Right? Any other questions? Okay, so let's maybe just take this example over here and try to compute the derivative. All right, let's say that f of x1, x2 is this particular function, e to the power x1 plus x2, x1 plus x2, x1 minus x2. What would the derivative of f evaluated at x1, x2 be equal to? Yeah, what is the 1/1th entry? It's the partial derivative of this with respect to x1, which is just e to the power x1 plus x2. What is the first row, second column? It's the partial derivative of this with respect to x2, which is the same thing, e to the power x1 plus x2. What is this? Yeah, so it's the partial derivative of this function with respect to x1, which is plus 1. What is the next entry? The partial derivative of this with respect to x2, which is again plus 1. Tell me, what is this entry? 1 minus 1. Right. That's it. All right. Now, if we're looking at functions from Rn to R, then the transpose of the derivative is, we'll call this the gradient of the function. So the gradient has the same dimensions as the function itself, as the vectors in the domain Rn. All right. Any questions? Yeah. We have to check the continuity at x1 comma x2. Yes.
For example, I have taken the first entry.
The first 1/1th entry, yes.
I have to say that x, each is on x1 plus x2 is continuous with respect to x1.
It's continuous with respect to x1 comma x2, right? So each of these partial derivatives is going to be a function of x1 through xn, right? So it has to be continuous at x1 through xn. Any other questions? Okay. Let's see some more examples to make sure that everything is firm in our mind. Let's take a very simple case. So f from Rn to R, let me say that f of x is equal to A transpose x plus b, where A is a fixed n-length vector and b is some constant. What is the derivative equal to? Is it the vector A? What are the dimensions of A? So A is a vector which has dimensions n cross 1, right? So the derivative is going to be A transpose, right? But if you want to do it formally, then how do you do it? Again, you take the Jacobian matrix. What is the partial derivative of f of x with respect to x1? It will just be a1, right? And what is the partial derivative of f with respect to x2? a2, and so on, right? So the Jacobian is simply the 1 cross n vector a1, a2, a3 up to an, which is equal to A transpose. All right, questions?
Dimensions.
The derivative always has, so if you have a function from Rn to Rm, it is an n by m matrix, right? The gradient of f at x is going to be the transpose of this, so it's going to be an n by 1 matrix. Right? Okay, let's take another example. So say that f now is from Rn to Rm, and f of x is a times x plus b. What is df of x? So A is an m by n matrix, B is an m by 1 vector, and x is an n by 1 vector. It will just turn out to be the matrix A.
Yes.
Yes. Again, how do you get this? Yeah, correct. You just try to evaluate each term. This first term will just be a11, a12, and so on up to a1n, and likewise. So it's straightforward, and this is exactly what happens in the one-dimensional case, right? So if you have f from R to R where f of x is equal to ax plus b, you know that the derivative is just equal to a, right? And the same thing happens in when you have a function from Rn to R as well as from Rn to Rm, right? So far everything is consistent. Okay. The L2 norm squared of x. Right? This is not very difficult because again you can write it as summation I equal to 1 to n of xi square, you can very easily find the Jacobian. What is the partial derivative of f with respect to x1? 2x1. With respect to x2? 2xn. So this is just 2 times x transpose. Alright? Again, dimensions, you have to be careful with the dimensions. But the gradient would be just 2 times x. This is exactly what you have in the one-dimensional case. The derivative of x square is just 2x. Any questions? Okay, let's see one more example. F from, again from Rn to R, but now f of x is x transpose ax. Note that I could write this x square or L2 norm of x square as x transpose x, right? So this is a slight generalization of the function that I had previously. Right? Now, if you, without trying to solve this, if you had to just guess what the gradient should be, what would you guess? 2ax, right? It's not. Right? The derivative is not 2ax. The gradient is not 2ax. Try to work it out. A has to be an n by n matrix. No. All right, so how do you go about trying to solve this? Let's try to get a sort of closed form expression for this in terms of the xi's, right? What is this? This is just x1 to xn times ax. What is the first entry of ax? Correct. So I can write it as summation j equal to 1 to n of a1j xj. Similarly, the ith entry is summation j equal to 1 to n aij xj. Right. So now when I multiply these together, I simply get summation I equal to 1 to n summation j equal to 1 to n of aij xi xj. All right, great. So now when I take the derivative with respect to let's say xi, right? Let's take some particular I. This is my f. What is the partial derivative of f with respect to some xi? What would this be equal to?
xj plus
Yes. Yep.
over a is of ai.
So effectively be summation j aij xj plus summation over j aji xj. All right. This is what it will turn out to be. I mean, think about it for a little while. All right. So this is nothing but summation overall j of aij plus aji times xj. Now can you tell me what is the derivative equal to? So what is, yeah, yes, so it's equal to a plus a transpose times x. Now if a is symmetric, right, then it is equal to 2 times a times x. But in general, if a is not symmetric, then the derivative is not 2ax, it is a plus a transpose times x. Right. Now again, if it's a function from r to r, then a is equal to a transpose, and therefore the derivative is just 2ax. So that's why you have to be a little careful when you go to higher dimensions. You can't just guess based on what you know from one dimension. All right. What is the gradient? Just I'm sorry. So there's a little bit of an error over here. It should have been x transpose times a plus a transpose, because my derivative should be a 1 by n vector. What is the gradient equal to? That is equal to A plus A transpose times X. Right, so this is a 1 by n matrix. This is n by 1. Any questions? The derivative, if you have a function from Rn to R, then the derivative should be 1 by n. Right? If it is from Rn to Rm, it should be m by n. Right? I mean, the way to think about it is the following. So if you take an f, right? You think about this particular, let's take this example of this function f. So this is a non-linear map from Rn to Rm. The derivative is simply a linear map from Rn to Rm. So it is just going to be an m by n matrix. That's it. And in fact, the derivative is just the linear approximation. You can think of the derivative as a linear approximation of f around that particular point x. Right? That's all it is. Any other questions? Okay. Now, this method is rather cumbersome, right? You can try to evaluate the derivative for a whole bunch of different functions, maintain a table, but as soon as I give you a more complicated function, do you have to compute the Jacobian every single time? That's not reasonable, right? So fortunately, what helps us is that just as we have a chain rule for derivatives in the one-dimensional case, we also have a more general chain rule for the derivative, right? And it's pretty natural, right? So suppose I have some function h, which is a composition of two functions f and g. So f is a function from, I think I should have written it the other way around. So let's say it is g of f of x. G of f of x. So f of x is a function from Rn to Rm in general, and g is a function from Rm to Rk. So h is going to be a function from Rn to Rk. All right. So in this case, the derivative of h evaluated at this point x is going to be the derivative of g evaluated at f of x times the derivative of f evaluated at x, which is exactly what you've seen in high school, right? And let's be a little careful and make sure that the dimensions all match, because after all, these are no longer real numbers, they are matrices, right? What are the dimensions of dg? This is a k cross m matrix. And what are the dimensions of df? This is an m by n matrix. And what should the dimension of dh be? This should be k cross n, and the product of these two is going to give you a k cross n matrix, so everything is fine. Right? So it's easier to describe the chain rule in terms of derivatives than it is in terms of gradients, because there's an easy way to see how the dimensions all match. All right, so now if I gave you a function that looked like this, so f of x is, let us say, e raised to x transpose ax, right? How do you find this? This is, I can write this as g of f of x, where what is g of y? It is e to the power y. So g is a function from r to r, right? And f is a function from Rn to R. So f of x is x transpose Ax. What is the derivative of f going to be equal to? It's the derivative of g evaluated at f of x times the derivative of f evaluated at x. What is the derivative of g? It's e power y, and you evaluate it at y equal to f of x, which is x transpose Ax. So this is just e to the power x transpose Ax times the derivative of f evaluated at x. What is the derivative of f? You've just seen that this is equal to x transpose times a plus a transpose. Right? This is much simpler. Right? So you can use the chain rule. I mean, this is a composition of two functions, but you can use the chain rule for the composition of any number of functions you want. It's easy to just simply generalize. All right. So let's maybe quickly see why the chain rule actually holds, right? And so before that, let me give another interpretation, another sort of mathematical way of thinking about the derivative, which will be useful to derive this particular chain rule, right? So recall, what is the derivative? The derivative is any function which satisfies limit as right. So I have limit as n tends to infinity of norm of f of y minus f of x minus df of x times y minus x divided by norm of y minus x. This should be equal to 0, right? Or I could also write this as, I'm sorry, as y tends to x. So I can also think of this as some vector epsilon tending to 0, f of x plus epsilon minus f of x minus df of x times the vector epsilon divided by norm of epsilon. This should be equal to 0. All right. So the slightly more geometric way of thinking about this is when epsilon is really, really small, you can write f of x plus epsilon as f of x plus df of x times epsilon plus some other vector epsilon prime, where epsilon prime depends on epsilon, but as the norm of epsilon goes to 0, the norm of epsilon prime also goes to 0, but faster than that of epsilon, right? For some epsilon prime such that the norm of epsilon prime divided by the norm of epsilon this is equal to 0. So epsilon prime tends to 0 faster than epsilon. All right, so basically these two are essentially equivalent. Okay, so this is sort of the first order approximation of f at x, right? So f of x plus d of x times epsilon, if you view this as a function of x, right? This is a linear function of epsilon, the right hand side, right? But in this exact function, this epsilon prime depends on epsilon, some complicated way, but all we are guaranteed is that epsilon prime decays to 0 faster than epsilon. Yeah, you can think of this as a Taylor series, kind of a the first order Taylor series expansion of f around x. All right, so this is what we have. Now let us look at, suppose I have h of x, which is g of f of x, and I want to derive the derivative of or derive an expression for the derivative of h of x. So I want h of x. So let me take a point x and look at a small neighborhood around it. So let's look at h of x plus epsilon, which is nothing but g of f of x plus epsilon. Now what is this? So epsilon, I know that f has a derivative at x, right? So I can write this as g of, what is f of x plus epsilon? It's equal to f of x plus the derivative of f at x times epsilon plus some epsilon prime. So let me write that out. So this is f of x plus df of x times epsilon plus epsilon prime, where this epsilon prime is something that decays faster, that decays to 0 faster than epsilon. Right? Is this okay? Fine. Now let me do the same for g. Let me view this. Let me view this whole thing as some, say, delta. All right, and try to expand this. So this would be g of f of x plus dg evaluated at f of x times delta plus some delta prime, where this delta prime decays to 0 faster than delta, right? But now let's just substitute for delta. This is g of f of x plus dg of f of x. Delta is nothing but df of x times epsilon. times epsilon plus epsilon prime plus delta prime. This is nothing but h of x plus dg of f of x times df of x times epsilon plus, so dg of f of x times epsilon prime. Now dg of f of x is something that depends only on x, it doesn't depend on epsilon, right? As epsilon tends to 0, dg of f of x times epsilon prime decays to 0 roughly as fast as epsilon prime, not epsilon, right? So this is something, whatever, let's say dg of f of x times epsilon prime plus delta prime. And delta prime decays to 0 faster than delta, so it should decay faster than epsilon, right? Roughly speaking. So both of these terms tend to 0 faster than epsilon. So I have h of x plus dg of f of x times df of x times epsilon plus something that decays to 0 faster than epsilon. Right? So therefore the derivative is just dg of f of x times df of x. Now if you want to do it very formally, you can use the same approach with the standard definition. Right? You can expand this dh of x in terms of this, show that they're close to each other and so on. Right? But this is a slightly easier way of showing that the derivative is equal to dg of f of x times df of x.
Why the third form tends to like delta prime tends to 0 faster than delta.
Delta prime tends to 0 faster than delta, correct? And but what is delta? Delta is some some term which is independent of epsilon times epsilon plus epsilon prime. So if it decays to 0 faster than epsilon,
Delta is decaying to 0 faster than
delta prime is decaying faster than delta, right? At what rate does delta tend to 0? Roughly like epsilon. Epsilon prime, but epsilon prime decays faster than epsilon, right? So delta decays roughly as fast as epsilon. So delta prime decays to 0 faster than epsilon, right? And we know that epsilon prime decays faster than epsilon. So both of these terms decay faster than epsilon.
epsilon is very small, but these terms tends.
Exactly. As epsilon tends to 0, you sort of divide by the norm of epsilon, then you essentially get something plus this, and these two terms just vanish. So the first order linear approximation would just be h of x plus dg of f of x times df of x times epsilon. Right? Any questions? All right. So let's try to quickly think about what is the geometric interpretation of the derivative or the gradient. Let's focus on functions from Rn to R, right? So consider an f from Rn to R. Now, based on what you've seen in high school, what is the interpretation? What is the geometric interpretation of the derivative of a function? The slope of the tangent at that particular point, right? So similarly, we can think of a tangent plane or a tangent hyperplane to a function in Rn. So firstly, what is a hyperplane in Rn? Rn, we'll define this in sort of two different ways. One which is slightly more general than the other, but essentially a hyperplane, you can think of it as just a linear function, right, or an affine function. So you have f of x to be equal to A transpose x plus b. All right, this defines a hyperplane. Okay. To develop some more intuition for the hyperplane itself, let's first look at the case where b is equal to 0. Right. So let's take f of x to just be A transpose x. Okay. Or in other words, let's take y is equal to A transpose x, and I'll rewrite this in the following way. So y is equal to A transpose x is the same as saying that A minus 1 transpose x y is equal to 0. Right? All I've done is just taken y to the other side, so I get A transpose x minus y is equal to 0. That is the same as saying that this big vector, this n plus 1 length vector A minus 1 transpose times xy is equal to 0. Right? So how do you define this hyperplane? The hyperplane is simply the set of all x, y in Rn plus 1 such that I'm sorry, this should not have a transpose over here. So this should be A transpose minus 1. Right? Or I should say A1, A minus 1 transpose x, y equal to 0. So y is, it's just a real number. X is an n length vector. And I stack these two to get an n plus 1 length vector. Alright, so this big vector is x1, x2, x3 up to xn followed by y. Similarly, this vector is a1, a2, a3 up to an followed by minus 1. Alright, it's fine so far. Great. What is this? What kind of an object is this? Okay, let me be a little more specific. If I had to ask you in terms of linear algebra, what kind of an object is this? What kind of a linear algebraic object is this? Affine transform? It's a set, right? What kind of a set is this? It's a null space of, so it's basically the right null space of this particular 1 by n plus 1 matrix, right? So what can you say about this particular object? It's a solution set, but it's also a subspace, right? And what is the dimension of this particular subspace? What is the dimension of the null space equal to? What are the dimensions of this particular matrix? N plus 1. So the dimension of this null space should be n plus 1 minus dimension of the whatever row space or column space. What is the dimension of this particular row space? What do you mean x vector, y vector? The matrix is fixed, right? Does it depend on A? How many say that the rank of this particular matrix depends on A? How many of you say that the rank of this particular matrix does not depend on what A is? What about the rest? What do you mean it does not? So why doesn't it depend on A? Is the question. Why for it? Can you say that for every 1 by n matrix?
Yes, the number of variables. Because there is only one of null space is minus rank of this.
So the question is, why is the rank of this equal to 1?
We can multiply any with minus 1, we can multiply.
Yeah, it's because there is at least one non-zero entry, right? That's the reason, right? So the rank is equal to 1. Therefore, what is the dimension of H? It is n, right? So if I'm looking at a function from, let's say, R2 to R, then this hyperplane is essentially a subspace. It's a two-dimensional subspace in R3, right? So the hyperplane is, or any linear function is, assuming that b is equal to 0. This is going to be an n minus, or it's going to be an n-dimensional subspace in Rn plus 1. Right? That's one way of thinking about it. Yeah. So what is the dimension of this particular subspace? So it's the right null space of this matrix, right? What is the rank of this? 1. What is the number of columns? N plus 1. So it's n plus 1 minus 1. So it's an n-dimensional subspace in Rn plus 1. Right? So if you have a function from R2 to R, then this is going to be a two-dimensional subspace in R3. And what is a two-dimensional subspace in R3? It's a plane. It's a plane passing through the origin. Right? If you look at a function from R to R, so if it's a function from R2 to R, then the hyperplane would be nothing but a plane passing through the origin. If f is from R to R, then what is a one-dimensional subspace? It's just a line, right? So hopefully that is clear, right? So in R2, a function from R2 to R, this essentially represents a plane, right? And in R1, it's just y is equal to ax plus b, which is just the equation of or y is equal to ax, which is just the equation of a straight line passing through the origin, right? If b is not equal to 0, then f from R2 to R, so A transpose x plus b, would be a plane but it would not pass through the origin. It would just be a shift, right? Similarly, if you have a function from R to R, then y is equal to ax plus b just represents a straight line. If b is non-zero, it does not pass through the origin, right? So that is one thing. Perhaps what is more interesting for us is what does A represent? All right. In R, that is clear. But now let us think about it in terms of this hyperplane. So let's go back. So this hyperplane is essentially the right null space of this particular vector. What does it mean? It means that every vector in the hyperplane is orthogonal to this particular vector, right? Because the inner product for every xy that belongs to this hyperplane, the dot product between this vector and this vector has to be equal to 0 by definition, right? So this vector is in fact the vector that is normal to the hyperplane, right? So A in some sense represents the direction that is orthogonal to the hyperplane, orthogonal to the plane. Right? And that's true for any affine function. So such a function is called affine. Any function of the form f of x is equal to a times x plus b is an affine function. So this in particular represents a hyperplane where A is, or in this case, this is the normal vector to the hyperplane. Right. So basically you take this plane that passes through the origin and you have a vector over here. So this vector would be A, and all the points satisfying ax equal to 0 would be this particular plane, right? That's assuming that b is equal to 0, right? If b is non-zero, then the corresponding hyperplane would just be a hyperplane that is parallel to this particular hyperplane, but just does not pass through the origin. All right. So in fact, maybe let's just take a look at this, see what it looks like visually. Right. Don't worry about what I'm writing over here, but let's try to visualize some of this. Let's take a vector, say 1 1 minus 1. Okay, so my A vector is just 1 comma 1. So let's take A to be 1 comma 1, which means that this particular vector is 1 1 minus 1. All right, and say A equal to vector of A. All right, it represents, say, this particular vector over here. Right? This is a visual representation of this vector, nothing more. Now let's try to plot the set of all xy such that, or x1 x2 such that A transpose x1 x2 is equal to 0. Right? So let's say I have uv, and what is y? Y is equal to A transpose x. So this is equal to u plus v. A transpose x is nothing but u plus v, or if you want to write it in that form, let's say x1 x2, y is equal to x1 plus x2, and x1, let's just plot it for a certain range, x1 say from -5 to 5, x2 from -5 to 5. All right, so this is nothing but a plane that passes through the origin. All right, and as you can see, this particular vector that we drew is orthogonal to this particular plane. Right? This vector is orthogonal to the plane. Now let's now take y is equal to x1 plus x2 plus a constant plus maybe 2. What do I get? Oops. So y is equal to x1 plus x2 plus 2 perhaps. What do I get? I get another plane that is parallel to this. So any change in B, all it does is it just shifts the hyperplane by some amount, but every such hyperplane is going to be normal to this particular direction. So this vector is going to be orthogonal to every such hyperplane, no matter how you choose B. So every vector here is going to be so basically it's perpendicular to the direction described by this particular vector. All right, is that okay? Fine. So now let's go back to this idea of the gradient. So how did we describe the gradient? So we have some function f of x, right? And what we wanted to do was take a first order linear approximation of f of x. I said that f of, say, y could be written as f of x plus say the derivative of f at x times y minus x plus something that decays faster than y minus x. Okay. So the following function h of y equals f of x plus df of x times y minus x. This is nothing but the derivative, or this is nothing but the tangent plane that passes through x. Let me write it in the following way. Let's write it as f of x minus df of x plus df of x times y. I've just rewritten things, nothing else over here. Okay? And the reason why I've written it is because I want to write it in the form b plus a transpose times x. So now what is b and what is a transpose? So B is anyway this quantity, f of x plus df of x times x. And what is A, what more importantly, what is A transpose? It's the derivative, or in other words, the normal vector A is equal to the gradient of f evaluated at x. Right? So the gradient at any point of the function, it gives you the normal vector to the tangent hyperplane at that particular point. Right? So let's maybe see an example. Right? Say f of x1, x2, this is equal to x1 square plus alpha x2 square. Okay, what is the gradient of f? Yeah, come on, this isn't hard. 2x1, 2 alpha x2, right? So this is the gradient. Right? So let's try to evaluate that. Let's fix a particular point. Okay. Let's fix a point. Let's say x is equal to, say, 1 comma 1. Right? Yes. So let me first plot the function itself, see what the function looks like. So let's say alpha is 1. Right, and I want to plot 1 x2. The function is x1 square plus alpha times x2 square. X1 taking the range, let's say minus 5 to 5, x2 5. So I get this particular function. It's a parabolic function, and depending on whether I choose a large alpha or a small alpha, just stretches in one particular direction. All right, that's just it. That's just it. Okay, so I get this. Now let's view the vector. Let's take another point, x, right? Let's take x1, x2 equal to 1 comma 1. So the vector point A, let's define point. Let's just take some point B equal to, say, 1 comma 1. What is the value of f at 1 comma 1? One plus alpha. Right, so this is this particular point over here, and what would be the vector A, that is the normal to the gradient, which is gradient of f minus 1, this would be 2 alpha minus 1, right? So this should be the normal to the hyperplane at this particular point. So let's say normal is going to be the point 2 alpha minus 1, right? So this would be the normal at this particular point. Here. Let's view this. So I have this surface and I have this particular point over here on the surface, right? That's my x. Now let me try to construct a hyperplane that is orthogonal to this particular vector over here, right? But still passes through this particular point, right? There happens to be an easy way to do it. So I just have to select a point and a perpendicular line, and it gives me the plane that is that passes through this point but is orthogonal to this particular vector, right? Let me call it. You see that this is indeed the tangent plane, right? It's tangential to this particular surface. It passes through the point, and what was the normal? What is the normal to this particular tangent plane? It's exactly gradient of f minus 1, the stacked vector, right? So that's a simple visualization of the tangent plane and how it corresponds, or what is the relationship between the tangent plane and the gradient, right, or the derivative. So really the geometric interpretation is that the gradient gives, in some sense, the slope of the tangent, but now the slope is determined in terms of the normal to the tangent plane in higher dimensions. All right? Any questions? Okay, so maybe let's stop here. In the next class, in the next class, I'll just deal with the second derivative and we conclude.